With this keynote, I would like to introduce you to a technique that one can use for the derivation of fragility functions, which are fundamental for the seismic risk assessment. I will briefly present some key components of the method with a case study to understand how the technique can be used. But before the presentation, I would like to play this 1-minute video to quickly recap the 2005 Kashmir earthquake and to develop their feelings when you are at the disaster site.
इतना शदीद था उसके झटके, बिल्डिंग बिल्कुल झूले की तरह झूल रही।
हम अपने बेडरूम से भागने की कोशिश कर रहे थे, सीढ़ियों पर पैर नहीं पड़ रहे थे, इतनी तेज सीढ़ियां हिल रही।
हर एक चेहरे पे खौफ था, एक्सट्रीम खौफ। अल्लाह अकबर की आवाजें, कलमा शरीफ की आवाज, इस तरह से लोग पढ़ रहे थे।
आज पाकिस्तान को और पूरे कौम को हमारी तारीख के सबसे बड़े ट्रेजेडी या सानिया का
साथ कश्मीर में मुजफ्फराबाद का जिला है, बाग का जिला है और रावलाकोट का कराकोरम हाईवे के साथ के इलाके जो हैं, बटग्राम है, पतन है, बट्टल है और एबटाबाद भी है, मानसरा है, गढ़ी हबीबुल्ला है, विशाम है, जहां पे कि काफी ज्यादा डैमेज हुआ।
रेक्टर स्केल पर इस ज़लज़ले की पैमाइश 7.6 थी, लेकिन तबाही का अंदाजा लगाने का तो कोई पैमाना ही न था।
19,400 के करीब लोग जा बहक हुए।
हलाक शुदगान की तादाद लगातार बढ़ रही है।
अब तक 25,000 अफराद के हलाक होने की तस्दीक हुई।
About 2.3 million people have been affected.
यूनिसेफ का कहना है कि ज़लज़ले से कम 17,000 बच्चे हलाक।
Of course, as an authority, we will never wish to have a crisis situation like this again, and one can easily realize that there is a very important role that engineers can play in reducing the risk. Because it's not the earthquake that kills people, but actually it's the building that collapses and causes fatalities. Here I'm showing two documents. One is published in Nature Hazard in 2014 that I authored with my past supervisors, Professor Kasserly from UT Peshawar, Professor Helen Crowley, and Professor Pinho from Rose School. They describe the methodology in more details. In another more recent article that I authored with Professor Deierlein from Stanford University, that shows the application of the method for derivation of fragility function for reinforced concrete frames. My talk is mainly based on this recent article to briefly describe the key components of the method. It's important to understand why the method is needed. We have to understand that there is no single value when we determine the seismic hazard and structural capacity. There are various possible outcomes, and we have to present the answer using the knowledge of probability. Unfortunately, for the same reasons, we cannot use the past observations, mostly the empirical methods, to predict the future, because the structure may change with time with the introduction of new materials and structure systems. So we need method and tools that can realistically simulate the nonlinear and dynamic response of the structures. This motivated me to develop the probabilistic nonlinear dynamic reliability-based method that is called the NDRM for seismic vulnerability assessment. And we will see in this presentation that it is used for the derivation of fragility functions. The ultimate goal of vulnerability assessment is to develop the structure fragility functions. It is illustrated in the figure on the left here. On the horizontal axis, we got values of ground motion intensity, which is peak ground acceleration in the present case. And on the vertical axis is showing the probability of exceedance of different damage states. We got slight damage, moderate damage, heavy damage, and collapse of the structures. The different curves give how often the structure exceeds each damage state for a given value of ground motion intensity. We can use these curves to obtain the friction of buildings attaining different damage states. For example, if we take the peak ground acceleration as 0.6, we can read that the probability of exceedance for slight damage is 0.94, and therefore moderate damage is 0.59. If we take the difference of these two, we can get the probability or the fraction of 0.35 that shows the fraction of buildings in slight damage state. In the same way, we can obtain the fraction of building in different damage states that we can use for the risk mapping and loss estimation. Mathematically, we can obtain these curves using the equation given on the right, where the probability of exceedance is shown as a standard normal cumulative distribution function that depends on the value of peak ground acceleration, that is defining the x-axis of the fragility functions, the median value of the PGA, where the structure damage state attain the probability of exceedance is 0.5, and the term beta, they define the standard deviation that represents the steepness of the fragility functions. Now, in this equation, the median value of the PGA and standard deviation are two constant, and the method can help to develop this for different limit states and for different structure systems. One can argue that codes are developed that can reduce the risk, but we have to say that codes and guidelines existed in the region since the 1931 Mw earthquake. And no matter if it was in the form of a simplified guideline or a more formal code, they have performed exceptionally well in saving lives and reducing property damage. However, these codes were followed in certain cases and were never disseminated to other parts of the country. And over the time, much of the control on constructions was lost in these areas. So despite the codes, many lives were lost in recent earthquakes. Now the next question is, why RC frames? Because we believe that reinforced concrete frames are ductile structures. However, if we refer to the damage statistic from the 2005 Kashmir earthquake, given in figure on the right, we can see the number of damages in RC frames were more than the brick masonry structures. And the reason is the presence of construction deficiencies in concrete constructions. This can be evident from the photo shown on the left, showing a 9-story frame completely collapsed in the earthquake, while other frames of almost similar characteristics are still intact. Of course, something was wrong with the construction because the ground motion intensity was the same for all the structures. And of course, even now, if we visit construction site, we can find a number of deficiencies in majority of the constructions. To report a few, I'm referring to the work of Yasir Fan Badrishi, who was a PhD student at UT Peshawar. He surveyed a number of construction sites and found some common deficiencies like poor quality concrete due to improper mix and improper compaction, using non-seismic hook, lack of ties in beam column joints, improper location and detailing of lap splices, and haphazard placement of stirrups at larger spacing. And we know that based on the past experience, that these were the main drivers increasing the vulnerability of RC frames. So how we can get there, how we can assess the vulnerability and obtain fragility functions. Of course, the very first thing is to know how much resistance and deformability are present in our structure system. And for that, it becomes important to perform experimentation on structure components and systems to obtain region-specific material properties. Here, I'm referring to the experimental work performed by Professor Crowley along with his students, testing beam column subassembly to understand the damage mechanism and obtain the force displacement historetic response shown in the figure on the right. The experimental result is compared with the response of a more standard strong column and weak beam counterpart system with an elastic beam column joint. We can clearly see that such an idealization can reasonably predict the stiffness and strength of the system, but it grossly overestimates the energy dissipation because of missing the pinching behavior of the historical response and the deterioration of strength and stiffness. And of course, to address that issue, we have to develop more realistic numerical prediction models. To understand the behavior of indigenous RC frames, we started this experimental program and we tested 12 full-scale beams at UT Peshawar. What we found interesting that there is a lot of deformability and flexibility coming from the fixing rotation due to inelastic extension of rebars, bond failure, and rebar slip. It was adding to the force displacement response of RC member, and that was resulting in the pinching behavior in the hysteretic response. So we use that information to guide numerical modeling technique to develop a more accurate nonlinear numerical model. So here what we did is to add a concentrated plasticity hinge at the ends of the member. The member was modeled with a more conventional inelastic fiber section based element that is available in most finite element programs like OpenSeas and Seismostruct. The hinge was assigned with a trilinear force displacement response to simulate various local damage mechanism For example, we have cracking, yielding, and rocking. The hinge was assigned a pinching behavior to simulating the opening and closing of the gap due to rocking. We studied the effectiveness of the additional nonlinear hinge in simulating the cyclic response of RC beams. Here we can see in the figure on the right a comparison of the numerical prediction to the experimental response for beam with most common reinforcement ratios. And here we can appreciate how the numerical model can mimic in simulating the cyclic response of the beam. Performance is relatively better for beam with low reinforcement ratio. However, some discrepancies can be observed in case of beams with higher reinforcement ratio. However, there is an obvious advantage in supplementing the fiber section-based element with an additional plasticity hinge to accurately predict the nonlinear response. So we came back here to our previous problem to see how this additional information can guide the numerical modeling of a more complex beam column joint. We modeled the beam and column member as an inelastic fiber section-based element. We added the same plastic hinge at the member ends, and also we added another nonlinear hinge to simulate the shear deformation of giant panel. We can consult a number of literature how to develop this shear deformation hinge for the panel. Now here in the figure on the right, we can see now a much better prediction of the cyclic response of beam column subassembly, where the improved numerical model can predict pinching in the hysteretic response and the deterioration of the strength and stiffness much better than the idealized model considering a strong column and weak beam model with elastic beam column joint. To better understand the impact of constructive deficiencies on the seismic behavior of frames, I myself, along with Professor Ahmad Khan and Dr. Rizwan, we started an experimental program to perform shaking table tests on frames. I want to play this 20-second video to show you the performance of a code-confirming frame subjected to seismic ground motions, which is Northridge 1994 in the present case. The outcomes of the shaking table test was the computation of the overstrength factor and the ductility of the frames. They collectively define the response modification factor given in the figure on the right. We can see that a code-confirming frame can achieve R factor close to what a code expects from a code-compliant structure. However, the factor reduces significantly when deficiencies are included in the frame. The objective of all the experimental testing programs was to collect information that can guide the numerical modeling of indigenous reinforced concrete frames. The numerical modeling technique was validated in predicting the displacement response of the frame. Here in the figure on the bottom right, we see an acceleration history that was input to the model. And in the figure on the top right, we can see the comparison of the predicted to experimental displacement response. We can see that the numerical model is doing very well in predicting the response of the frame. Once we develop the numerical modeling technique for analysis, the next question is what structures are analyzed for vulnerability assessment and derivation of fragility functions that are applicable to a portfolio of structures at a large scale. So we generated a number of structure models based on the data collected from the literature review and from the field observations. In present case, we consulted a number of design offices in northern areas of Pakistan, especially Peshawar and Islamabad, to get the variation in the constructions. The structures were classified based on the height, for example, low rise that represents 1 to 3 story, mid rise that represents 4 to 7 stories, and high rise structures having stories more than 8. We subdivided these into 3 categories, including good quality constructions, that is representing high code structures, typical construction that represents moderate code structures, and poor quality constructions that represents low code structures. This type of idealization is also proposed in the vulnerability assessment guidelines of global earthquake model. We also need a set of ground motions for response history analysis of selected frames. For that, we can use the peer ground motion database. I'm showing a snapshot given on the left. We can see a search engine that requires certain parameters to look for the appropriate ground motions. We can choose the parameter like moment magnitude, the side distance, VS30, the duration of the ground motion, similar to what we can expect for our tectonic regions. So here in the figure on the right, we are showing the acceleration response spectra for a set of 24 ground motions that were selected for analysis of our selected structures. The next important step is the development of damage scale based on experimental tests. In present case, we use the data from the 6 shaking table tests performed on RC frames. The objective was to develop the base shear and lateral displacement response of the building and to identify various damage states, for instance, slight damage, moderate damage, heavy damage, and the collapse. Using that information, we proposed drift values for each damage state. Some adjustment was proposed to take into effect the variation due to higher gravity loads for mid and high-rise frames. Here is the final framework of the NDRM that combines all the information. We prepared the region-specific numerical models and took the selected set of ground motions that was input to the numerical models. We linearly scaled the ground motions for dynamic analysis. The objective here is to obtain the median value of the story drift demand and the associated standard deviation of the log values of the drift. The drift demand and drift capacity are combined through convolution to obtain the probability of exceedance. The method uses the hasofer-lind reliability index to compute the probability of exceedance of different damage states at a given PGA. We can obtain the values of the probability of exceedance at different values of PGA to construct the fragility function given in the figure on the bottom right. Using the procedure, we derive fragility functions of all the 9 groups of structures, including low-rise, mid-rise, and high-rise structures. Let's focus on fragility function of a low-rise structures. So here in the figure on the left, we have fragility of low-rise structure of good quality constructions or high code structures. And in the figure on the right, we have fragility of low-rise structures of poor quality constructions or low code structures. Taking the PGA value equal to 0.6, which roughly correspond to the MCE level ground motions, we can see that the probability of exceedance for different damage states is much lower in case of good quality construction in comparison to the low quality constructions. And this is because of the higher resistance and ductility of good quality constructions. We can also look at the damage matrices using the fragility functions. So here we obtain matrices for both the DBE and MCE level ground motions. Let's have a close look, especially at the low-rise and high-rise structures. What is interesting to note here that the probability of collapse for both the low-rise and high-rise structure is close to 0.1, which is the value we can expect for a code-conforming structures. However, the probability of exceedance increase as the quality of construction decline from good to typical to poor, as the required strength and ductility of these structures reduce significantly. We also look at how these functions can compare with the functions given in the HAZUS framework, which is a more standard method used in the United States and other parts of the world for risk assessment. Let's focus on few structures here. Here we look at the 2-story and 12-story good quality constructions or code conforming structures. If we look at the collapse fragility, especially the DS4, we can see that both methods give very similar results. However, if we compare other damage states, especially moderate and heavy damage states, we can see some differences. Of course, it's because of the differences in the damage scale of the two methods. Our damage scale was based on shaking table testing our 2-story frames, while that of HAZUS is not much clarified. So this outcome encourages us to develop our own region-specific fragility functions. We also look at few more structures to see some merit in our derived fragility functions. So here we can easily see that in some cases the HAZUS will give quite different results for damage evaluation. For example, in case of 5-story typical, it is underestimating the probabilities, while in case of the 12-story poor, it is overestimating the probability. The derived fragility functions can be used to obtain the repair cost ratio. It basically tells how much repair cost is required after damaging earthquake. In this case, we can see that both methods give quite similar results with some slight underprediction and slight overprediction. If we look closely at the high-rise structures, we can see that HAZUS only slightly overestimate the repair cost ratio, but it significantly overestimate the repair cost ratio in case of low-code structures. So this clearly demonstrates that there is a work in developing region-specific fragility functions. To conclude, I would like to share some of the observations made over the course of this research. The first and most important learning is that besides developing code, it is strongly necessary to enforce code. Only then it can be promising in reducing the risk. Next, as we see the comparison of our fragility functions with those given in the HAZUS framework reveals similarity in some cases, but also differences in few other cases. That encourages the development of region-specific fragility functions. Also, as you notice, the proposed method is highly dependent on the accuracy of the numerical models. Thus, it is important to perform experimentation on region-specific materials and structures. Finally, I will recommend that the research and development institutions should upgrade the computation capabilities to accommodate more computation programs and tools to advance research in the universities. I'm grateful to my past collaborators and students who played a key role in pushing forward the research and development activities at UT Peshawar that helped me and other students in achieving various milestones. Of course, this work was not possible without their hard work and dedication. I'm also thankful to the United States Education Foundation for sponsoring my appointment at Stanford University. This exciting journey was not possible without their generous support. So this was all from my side. Thank you.